All right, hi everybody. Thanks for being here. This session we're going to talk about a series of techniques and methodologies that we use to reverse engineer wireless communication protocols. My name is Matt Knight. This is Marc Newlin. We're both security researchers with Bastille Networks. We're really excited about wireless technologies and software-defined radio because wireless systems are everywhere. It's 2017, and following the growth of mobile and IoT, more and more devices are getting connected every year at an increasingly accelerating pace. The Cisco Internet Business Solutions Group has a figure that I really like. They stated that in 2015 there were 20 billion devices connected to the internet in some way, and they project that by 2020 that number will increase to 50 billion. And as we know, fewer and fewer of those devices are being connected with wires every year. So I think Don had a lot to say about the Internet of Things in his keynote this morning, and he described it as security researchers' favorite four-letter word, which I think is really great. But we all know that when we're talking about the Internet of Things, we're really referring to connected embedded devices. And as we've seen in headlines and security publications just about every week, these smart devices are usually pretty dumb. And there are good reasons for it. It's because these embedded systems are really built around compromise. Oftentimes they have to be manufactured in volume, so there are restrictions on how large they can be or how expensive their BOM can be. Oftentimes they're battery powered, which limits the types of computation you can do on it. And additionally, they are often deployed in challenging deployment scenarios. And to illustrate one, I'll draw your attention to the picture on the right there. In frame but not visible are three literal embedded systems. They're embedded in concrete. So you might imagine that it's a much more difficult environment than, say, your traditional, a traditional piece of office or IT equipment. Additionally, these devices are often very hard to patch, whether it's from using one-time programmable memory that cannot be rewritten or complicated vendor and supply chain relationships. It can be very hard to get software updates out to the actual devices, even if they are made available. So you can argue that these embedded systems are really vulnerable by virtue and by the manner in which they are constrained. So to illustrate why wireless security is relevant, I'm just going to briefly mention two high-profile attacks that occurred in the last couple of years, just to illustrate the types of vulnerabilities that exist and really what's possible. So in 2014, our colleague Logan Lamb discovered a series of vulnerabilities in the wireless link that connects sensors to home security panels. And the way these work is the sensors are these very simple one-way wireless communication protocols that basically just broadcast their state whenever the state changes. And then the panel contains the state machine that's used to determine when to call home to trigger an alarm. Since it's a one-way link, there's no ACK, so the sensor can't know that it got through and can't know to retry if the message gets denied. So Logan was able to pretty trivially jam this channel so that alarms wouldn't get reported. So you could just walk into somebody's house and it's as if they didn't have a home security system at all. He was also able to inject commands into the system to do things like trigger false alarms and all sorts of nasty things as well. And that was made possible because it was this legacy link that was unencrypted, unauthenticated, and just nobody had thought to look at it yet. The second vulnerability I'll mention is a series of attacks that Marc here discovered in 2015. And Marc spent a lot of time looking at the wireless link that connects non-Bluetooth wireless mice and keyboards to the dongle that gets plugged into the computer to connect them. So vendors often use this non-Bluetooth protocol called NRF24 because it's less expensive than Bluetooth. There's no licensing associated with it. However, it really implements just a physical layer. There's no layer 2 and therefore no security built into it as well, and that's left up to the vendor. And by analyzing a number of these devices, Marc was able to find problems with the implementation of just about every vendor-specific security model that was put in there. And in many cases, they didn't even implement security at all. So it was just plain text being sent over the air. So this enabled things like command injection, running commands at arbitrary commands at whatever the permissions level the currently logged in user was, and also doing things like eavesdropping, which you could use to sniff passwords or credit card numbers or things like that. And I'll hand it off to Marc.
So at the IoT Village at DEF CON last year, Matt and I gave a talk where we reverse engineered a wireless toy drone. And we got some good feedback from that talk, and we included a section in there where we kind of went over the fundamentals of how we reverse engineer these type of devices, and people seem to really enjoy that content. But we got a lot of feedback that indicated people think RF is intimidating or too academic or requires an EE degree, which is really not the case. So Matt only has a bachelor's degree, I have no college education, yet we're both able to leverage existing open source hardware and software tools to do some pretty cool work in the space. So our premise is that you have no PhD, that is no problem. So we're going to start by providing some background on the hardware and software tools we like to use. We're then going to provide a little bit of background on some of the fundamental RF concepts that are necessary to understand the rest of the talk. We're then going to introduce an RF reverse engineering workflow that we use to reverse engineer wireless devices. And this is the really meat of the talk. And the premise is that we can use this workflow to reverse engineer any wireless system. And then we're going to demonstrate this workflow by going through and looking at a few different devices. And we're not going to get into any DSP topics because you really don't need to understand that to do this type of work. So when you're looking into getting into this wireless hacking, you may want to know, what do you need to know, what tools do you need, what hardware do you need to buy. And it's nice because the barriers to entry are quite low now. So hardware and software-defined radios are getting quite inexpensive. There's a great open source ecosystem around this. And on the hardware side, we have both hardware and software-defined radios. So a hardware-defined radio is something like the Bluetooth modem in your phone, cellular modem, Wi-Fi radio, these kind of things. And in this case, you have all of the logic that speaks a certain protocol is baked into silicon. We then have software-defined radios, which are a flexible RF front-end. So this is a radio you can tune to different set of frequencies, set to different channel bandwidths, and all this raw radio data gets piped to your host computer. So instead of having the logic baked into silicon, the logic that speaks each individual protocol is then implemented in an FPGA or in software. And this is really, really great for doing research and reverse engineering because it's possible to iterate quickly. Instead of making a hardware change to tweak the protocol, it's just a tweak in software. So on the software side, we're big fans of GNU Radio. This is an open source digital signal processing suite, and this abstracts away a lot of the math that you don't actually need to understand. So this is a very robust tool, and you can use this to take information from open source intelligence to build radio transceivers. Matt and I have both contributed to GNU Radio. Matt reverse engineered the LoRa protocol and released GR LoRa, which is a software-defined radio transceiver for LoRa. I've done a lot of work with these Nordic NRF24 devices and released a GR Nordic module. And then there's Baudline and Spectrum, FOSS4, and Universal Radio Hacker are for good spectrum visualization and analysis tools we like to use. On the hardware side, there's the BlueStack on Linux, good Bluetooth stack. There's libubertooth for the Ubertooth. There's Killer Bee for doing 802.15.4 work with App Emote and the Rs USB stick. And then I've done some work releasing open source firmware and software for these NRF24 devices. And the nice thing is that because this ecosystem of hardware and software tools is so robust, we can leverage all this existing work and stand on the shoulders of giants and only have to focus on the meat of the reverse engineering process, which we're all hopefully comfortable with. So now Matt's going to take you through some of the basic RF fundamentals we need to know.
All right, so as Mark mentioned, really the purpose of this next section is to provide just enough context about the wireless domain to be able to understand the rest of the reverse engineering process and methodology. So when we discuss wireless communication protocols, we're invariably talking about or involving the physical layer of our familiar communications model. And this refers to the lowest layer in the stack. And in wired protocols, it defines how your digital ones and zeros get mapped into voltage, timing, and wiring. However, in wireless systems, it instead refers to how your ones and zeros get mapped into the RF medium, patterns of energy that's being sent over the electromagnetic spectrum. So our friend Tom Rondo, who's the former GNU Radio project lead, but is now a DARPA program manager, loves to proclaim that RF is one of the four fundamental forces of the universe, and that with radio, we as engineers and as hackers get to manipulate it. So that's kind of sweet. But the radio frequency is essentially just the electromagnetic energy that is around us all the time. We can visualize it by putting together this picture called a spectrogram, or a waterfall plot. Essentially, what this does is it plots out all the different frequencies that compose the RF domain on the x-axis, time in the y-axis, and then power in the z-axis. So it's a nice way to be able to see what's actually happening on this complicated shared medium. So RF can be manipulated using a device called a radio. And as Mark mentioned, radios can either be hardware defined, where the protocol, the RF and protocol processing circuitry and logic is baked into silicon, as is the case with the LoRa radio on top of that picture, or it can be software defined, where instead you use a flexible piece of silicon kind of at the front end, and then you offload raw radio samples back to some sort of a processor to implement the radio specific components and protocol specific components and software. That can either be a general purpose CPU or something more specialized like an FPGA. So when we talk about what makes a wireless PHY, kind of the core element here is the modulation. The modulation is a function that defines how these digital ones and zeros get mapped into RF energy. And there are three kind of physical parameters that are unique to the RF domain that we can modulate. We can modulate amplitude, which is the power of the signal, the frequency, which is the rate at which the signal is oscillating, or the phase, which is the offset into the periodic signal at which the signal begins or ends. And of course, we can modulate, some combination of these kind of in conjunction or in coordination to make more complicated PHYs. But really, these are the three elements on which all modulations are built upon. So modulators can modulate either analog, continuous time, or digital, discrete time information. But we're going to be talking about digital modulation modes. And the key component of this is this notion of a symbol. And this is the most important concept to take away from this section, is this notion of a symbol. And the symbol essentially describes a discretely sampled RF energy state that represents some quantity of information. So when you hear the term symbol, just think that it's a state that exists in the wireless medium that represents a 1 or a 0 or some combinations of 1s and 0s. So it's really just a state. And we'll describe it in the next 2 slides. So I'm going to briefly describe 2 very common wireless IoT PHYs. The first is frequency shift keying, which is shown in the spectrogram on top. And the second is amplitude shift keying, which is shown in the spectrogram on the bottom. So they're fairly simple. I mentioned the 3 elements that you can modulate: amplitude, frequency, and phase. Each modulation here only modulates one of them. So the top picture, FSK, frequency shift keying, obviously modulates the frequency. And I think it's pretty intuitive what's happening in this picture. The signal alternates between 2 frequencies. And if it dwells on one frequency for some amount of time, that represents a 0. And if it dwells on the other, it represents a 1. The picture on the bottom, I think, is also fairly intuitive. As you can see, the frequency is constant. It doesn't change. And instead, a 1 or a 0 is denoted by the signal being on or present at a discretely sampled moment in time or off. IoT PHYs can get more, or wireless PHYs can get more complicated. We have spread spectrum modulations where your data gets encoded at a higher rate and occupies more spectrum than is required to transmit that amount of information. And the advantage here is that you can make PHYs that are more resilient to RF noise and interference. So 2 common examples that you'll see in the IoT are 802.15.4, which is the physical and MAC layer that Zigbee is built on. There's a picture of what that looks like in the spectrum on top there. And also LoRa, which is a more modern PHY, which is shown in the picture on the bottom there. So both of these physical layers consume a lot more bandwidth than is actually required to transmit the amount of information that they're transmitting. But the designers instead choose to use more than is necessary to basically increase the resiliency of these different transmissions against interference. So radios have 2 functions. They can either transmit or receive, but if a chipset can do both, we call it a transceiver. And when it comes to reverse engineering these systems, our main objective is to figure out how the data, the 1s and 0s, gets mapped into symbols. So as we approach it as reverse engineers, it really boils down to building receivers, basically getting really good at listening to these protocols, figuring out how they work, and then re-implementing a receiver. So this brings us to our wireless reverse engineering methodology, and this is what we're really excited to share with you all today. What we're going to do is we're going to walk through and introduce a series of steps that you'll be able to take and apply to just about any low complexity wireless IoT PHY to basically provide structure to the reverse engineering process. And we'll show you that by following this process, you'll be able to remove a lot of the math and a lot of the really kind of hard conceptual stuff to make a lot of this really plug and play. But before we get into that, I want to do a little exercise. So here's a picture of a spectrogram of an arbitrary signal, and I'm just going to throw it out to you and ask some people to just take a look at it and volunteer any observations you might have about it. Yeah, so I've heard a couple people say frequency shift keying, as is indicated by the fact that the signal occupies more than one frequency throughout this capture. How many frequencies are represented here? 2, exactly. So it's 2 FSK modulation. Now, can we make any observations about the channel? Is there one center frequency here, or are there multiple? There's just one, yeah. So there are 2 frequencies that the signal shifts about, but it's all kind of centered around the same segment of the spectrum. And what can we say about the periodicity of the signal? Is there anything to observe there? Yeah, so it looks like there are kind of two different segments in this transmission. So up top, the signal alternates back and forth between the two frequencies in a very predictable, consistent way. And then once we get down towards the bottom, it changes, and that alternating pattern becomes a little more erratic. And we'll talk about what that is momentarily. So let's formalize this process that we just discussed and put some kind of concrete, reproducible steps behind this. So step one to reverse engineering a wireless protocol is to characterize the channel. And there are really two key things that we're looking to identify here. First is where on the spectrum the signal lives, so what is its center frequency? And the second is how wide the channel is. So when we talk about the channel width, we're referring to the amount of spectrum that the signal traverses. So for FSK, the width of the channel is described by the deviation of the protocol, which is the distance in hertz between the two frequencies that it alternates between. And the third note there is kind of a caveat on identifying the center frequency, and that's that you may have a frequency hopping protocol where the center frequency may change, may jump around, so you might have to track that. So the second element here is to identify the modulation. And again, the modulation is the function that describes how your digital ones and zeros get mapped back into RF energy. And this is by far the scariest, most intimidating, math-heavy part of this process, and is definitely the most daunting. However, once you realize that most of these modulations are really just variants on a small handful of functions, it really becomes a lot less intimidating. So as you begin to work with wireless systems, you'll very quickly develop intuition for recognizing modulations based on a spectrogram or through some other means of inspecting it. However, until we get that level of comfort, we'll be able to do this purely by using open source intelligence and documentation. We'll be able to pull it out of the docs. Step 3 is to determine the symbol rate. And the symbol rate is how often that symbol state changes. Essentially, how often the state that we're measuring in the wireless medium changes. And we can either get this out of open source intelligence and documentation, or we can use tools to measure it. And we'll walk through examples of this momentarily. Step 4 is to synchronize, and that essentially exploits the periodicity that we observed in the example signal we put up earlier. So we noted that the top half of the signal had a very predictable pattern of oscillation. In the bottom, it became a little more erratic. That's because the top half of that signal was a preamble. And a preamble is essentially a pattern that tells a receiver that data is about to follow over an on-air transmission. It's also used for clock recovery. That's a little more complicated. We'll mention that briefly, but we won't go into too much detail there. But oftentimes the preamble is paired with the start of frame delimiter. The start of frame delimiter is essentially a constant static value that tells the receiver the preamble is over, and everything that follows from here on out is data. So essentially the preamble and the start of frame delimiter are used to get the receiver to synchronize to the transmitter and figure out when to start sampling out those symbols. And some combination of these elements are present in essentially every wireless physical layer. Sometimes you might just have a preamble, sometimes it might just be an SFD. Oftentimes you'll see them both used in conjunction. But there will always be something like this for you to rely on. And finally, step 5 is to extract the symbols. And that's basically demapping the symbols that we've measured back into the data that they represent. And that's based on the modulation and encoding of the protocol and other things like that. And that's the last step before you win. We'll expound more on that later. So these are kind of the 5 core steps, and we're going to show it to you in action with a series of live demos. But before we do, Marc is going to talk about how open source intelligence can make your life easier.
So I am a huge fan of open source intelligence because it makes it easier to be lazy. So as engineers, if we can offload our work to somebody else or get information from open sources, it saves us time. So whenever you're selling a device with a wireless transmitter in Europe or the US, you typically have to have regulatory data that's filed with the FCC or other bodies. And this data describes the physical properties of how a device operates. That would be its power, what frequency it operates on in the spectrum, in some cases modulation and other data. And this can be a good way to jumpstart the reverse engineering process. There are also often times where you have devices which use common off-the-shelf transceivers. So it's easier to use a part from TI or CC or Nordic or somebody else rather than roll your own ASIC. So if you're using one of these off-the-shelf transceivers, you can open up a device, find the chip number, and oftentimes find a data sheet, which will usually tell you the modulation, other data, perhaps the packet format, and so forth. You can also leverage patents, other just random Google foo. And so it's easy to always start this process by doing some open source intelligence and find all the data you can before you do some blind reverse engineering and really save a lot of time that way. If you're interested to learn more about the OSINT process, I gave a talk at Hack in the Box Amsterdam last year about applying this regulatory data specifically to the RF reverse engineering process. So we're going to insert OSINT research as our step 0, and we're always going to start on these projects with some open source intelligence. And now Matt's going to walk you through this lovely home security siren.
All right. So I'm going to be taking you through the first device we're going to show off, live demo we're going to go through is this lovely home security siren. It's made by the Fortress Security Store. And basically it's a combined magnetic door sensor, like what you might apply to the back of your door in a home security system, and an extremely loud, super annoying siren. So the idea is you would stick this thing on the back of your door, you would click it, you would arm it with the little key fob there when you leave the house, and if somebody opened your door, it would annoy the hell out of them. So let's reverse engineer this wireless protocol and figure out how it works. So step 0, open source intelligence, always start there. So the first thing we're going to look for is an FCC ID. In the US, if a product is sold in the US, it has to go through FCC certification, and there are different requirements on whether or not the device has to bear the FCC ID printed on itself. This device should have an FCC ID, but for some reason does not. Thank you, China. So instead I had to resort to some other methods. So I Googled around, different combinations of Fortress Security Store and the product name and things like that. And I found a bunch of references to other devices, but none to this device. So I decided to go a little bit deeper, crack the case of the transmitter and pull out the circuit board. So the top side of the board's not that interesting, just a couple buttons and passives and a trace antenna. But the bottom side contains a pretty big hint. There's some power circuitry and things like that, but then there's this chip that's silkscreen, the EV1527. So if you take that and you plug that into Google, you win. The top result is the data sheet for this device. The package matches, it looks just like it. And then further down in the documentation, it actually gives us a data format. So this is a ton of information. First of all, it tells us that it uses a combined preamble and startup frame delimiter, so they're kind of one and the same. That is basically one symbol where, one valued symbol and then 31 zero valued symbols. And then it also describes an encoding process. And what this suggests is that this is an on-off keyed modulation, or most likely is. So we've done a little bit of open source intelligence research, and we've identified a likely candidate for the modulation. We've gotten some huge clues for how we're going to approach synchronizing against these transmissions, and we've also figured out the encoding scheme. So a little bit of research has gotten us quite a bit. But what we're missing is the channel. So instead of being able to pull this out of the documentation, we're going to have to go and actually figure this out ourselves. So we can capture some raw radio information with our SDR and pipe it into a spectrum analyzer program. This is Baudline. I'm a huge fan of it. And then we can go and look through common frequency bands where these types of devices often transmit. So in the US, these are called the ISM bands, which stands for Industrial, Scientific, and Medical. They have pretty lax regulatory and licensing requirements, so devices can operate very permissibly there. The most common ones you'll see are like 315 and 345, 433. 2.4 gigahertz obviously is where Wi-Fi and Bluetooth live. That's a really busy one. And then if you're in the EU, you'll have 868 in addition. And then in the US, instead of having 868, you'll have 915. So I hopped through a few of these and saw the signal living in the 433 megahertz band, just below 434 megahertz. And again, we have a single carrier present, which confirms that it's some sort of amplitude shift keying or on-off keying modulation rather than a frequency-based modulation. So we've confirmed the modulation and identified the channel just by doing a little bit of poking around in the spectrum. And again, a lot of that was really motivated by the information that we learned from the documentation first. So step 3 is to determine the symbol rate. So I'll take that same capture that I just took, and this time I'm going to load it into Inspectrum, which is a really powerful open source spectrum analysis tool. Spectrum has a really awesome feature where you can basically drop cursors on top of your waveform and basically drag them around to figure out timing information about the symbols here. So by using the cursor tool and just doing this really nice and visually, I'm able to determine that the symbol rate is approximately 4.23 kilohertz. So That's a ton of information right there, doing no math, I'll mention. So now we have to get a little more technical. And we have to actually start to think about how we're going to implement this in software to be able to get bits out of this wireless protocol. So what I like to do is I like to kind of split this problem in two. And I like to implement the kind of math and DSP heavy functions in GNU Radio, which is a really powerful signal processing tool that Marc mentioned earlier. And then to implement the last two steps, the synchronization and the symbol extraction in Python or in a language that's a little easier to iterate on. And I think that those later two, technically you can do all of this in GNU Radio. GNU Radio has the tools to be able to synchronize and packetize data and things like that. But I think it's nice and natural to be able to iterate through things in a language like Python or an environment that is a little more fast and flexible. So here's the flow graph I put together. It looks complicated, but it's really not. And furthermore, this flow graph you'll be able to take and apply to any on-off keyed modulation just by replacing the values of some variables that are in here. And we're going to release this online later. The first block is the driver for the radio. And the second is basically just channelizing the signal, just taking the signal and aligning it with the center of the band. That second block, labeled number 2, is essentially our amplitude shift keying demodulation. The complex to mag squared is taking the power of the signal, and then the 10 log 10 block is basically converting it from whatever complex to mag squared produces to dB, which is a more normalized scale. The third block there, labeled clock recovery MM, basically converts, resamples the signal from our sample rate down to our symbol rate. It looks really complicated. There are 5 floating point values there. I'll tell you that values 2 through 5 are their defaults as they come populated in GNU Radio. And the first value, omega, is filled in by some variables that you'll be able to reconfigure with information that you glean from documentation. So basically just stating that these are all default values, and like the one that's not is just straight out of documentation. And then block 4 basically converts our power levels into our binary 1s and 0s that we're expecting. Finally, the last step with a file sync is just taking those 1s and 0s and pushing them out to a named pipe on this computer so that it can be pulled in through Python. So steps 4 and 5 are implemented in Python. I'll just briefly describe it to you now. Essentially, we're going to synchronize against the stream of symbols by looking for the preamble that we glean from the documentation. And that's a single 1-valued symbol followed by 31 0-valued symbols. Once that matches, we're going to read out some number of symbols that is determined based on kind of empirical observation. So by using Inspectrum and timing it out, I saw that the packet is around 100 symbols long. So I'm just going to grab a buffer of 100 symbols and work with that. Then using the encoding information that I found in the documentation, I'm going to demap those encoded symbols back into the 1s and 0s we expect. So for 1110, that maps back into a logical 1, and for 1000, that maps back into a logical 0. And then finally, we can look for patterns in this and try to figure out what the structure of the frame is. It turns out that this is super simple. Essentially, we have a 20-bit unique address that's unique to each transmitter, and then 4 bits describing the state that's desired based on the button press. So time for a live demo. What could go wrong? So first I'm going to show you receiving. So I'm going to start up the DSP portion of that flow graph that I showed you already. So I'm going to hit this button and crank it up. And then I'm going to jump over to a shell here, and I'm going to run the decoder. And then I can, basically press the buttons on these different devices, and you see that the state's changing. And then I can jump over to this second device and press it, and you see the address changes. And then we can also implement transmitters using software-defined radio as well. And I'm not going to walk through the transmitter just in the interest of time. I will say that implementing transmitters is a lot easier because you don't have to worry about synchronization. You can basically just transmit arbitrarily and not worry about the timing. And transmitting is really where it gets fun because this is where you get to do super annoying things like make lots of noise. So I'm going to warn you, it's going to get very loud. I'm going to wear some hearing protection. Just prepare yourselves. Now I'll start the other one. Yeah, I'll turn them both off. One more time. There we go. So you can do super annoying things like that using software-defined radio. How's everybody's hearing? Thank you. You all signed the waiver, right? Cool. So with that, I'm going to hand it over to Marc, and he's going to take you through this barcode scanner.
Okay, so now we're going to talk about this wireless barcode scanner from the well-known company Wone Nice. This was just the cheapest wireless barcode scanner I could get on Amazon. And this is advertised as a 433 megahertz device. There's no FCC ID on the scanner or the USB dongle that receives it. And the way this device operates, the USB dongle plugs into the computer, it registers itself as a USB HID keyboard, and then this sends HID commands for injecting keystrokes into the dongle, which, well, could go wrong. So we're going to start with some open source intelligence. And we don't have an FCC ID, so we can't use that documentation, but it did come with the user manual. And in here it does say a 433 megahertz center frequency, so that gives us some data about our channel. And then I opened up the enclosure for the dongle, and you can't quite make it out in the picture there, but the smaller IC is an RFIC from Silicon Labs called the SI4432. This is great because when we have a known chip, we usually have a data sheet. So next we can look up the data sheet here, and this has some potentially useful information, but not that much in this case. So we can see it has a frequency range in this model between 240 and 930 megahertz. It has 3 different modulation types, wide data rate band. So we really don't know how this thing is configured, but we know what it's potentially capable of. We also see that it has a configurable packet header, so all of this tells us that it could be doing really anything. So that means we need to start breaking out a radio. So here we have the packet structure. Again, lots of reconfigurability, huge preamble range, huge configurable sync word, optional header and packet length, unknown data length, and then optional CRC. And then we also have CRCs that can be applied to part or all of the packet. It can be whitened or not. It can be Manchester encoded or not. So we really don't know a whole lot yet. So we do know that it's 432 megahertz center frequency. Well, we think. So next I brought up a baud line with an SDR, and this is a flow graph on the left with USRP source is the data coming in from the software-defined radio. And then we have a baud line sync on the right, and this is what receives the data from the SDR and pipes it into baud line, which is the spectrogram we see on the right. And you'll notice in the flow graph, it's actually 434 megahertz, and this is because the center frequency was listed incorrectly in the marketing materials and the user manual, off by 1 megahertz. So we have this 434 megahertz centered channel. And on the right, we have what looks like a packet coming from the barcode scanner to the dongle, and then below that, an ACK coming from the dongle back to the barcode scanner. And then we zoom in on that on the next spectrogram on the left there, and we can see that it appears to be frequency shift keying. It's just going back and forth between these two frequencies. So now we're able to pretty quickly visually identify this type of modulation, and you'll get more comfortable with this as time goes on. So now we know that it's a 434 megahertz channel, and that is frequency shift keying. So now we're going to try and figure out what the symbol rate is. And for that, we're going to start by capturing some IQ data. So this is a tool called UHD-RXC file that you can use with a USRP software-defined radio. And what this is going to do is just take 10 seconds of data at a 10 megahertz sample rate, centered at 434 megahertz, and write that to disk. And what I did in preparation for this is record 3 different IQ captures, one with each of 3 different barcodes, so we have some data to compare. So I take the first capture and load it up in Inspectrum, and this is what Matt had used earlier here. So on the bottom, we have this frequency plot, which shows us the oscillation of the frequency between the 2 values. And then we can use the cursors tool to basically line up these vertical lines with these frequency shifts, and that tells us what the symbol rate is. So we have a 38.4 kilohertz symbol rate. So now we know the center frequency, we know the modulation type, and we know the symbol rate. So now we need to figure out what's actually in these packets. There's a tool called Universal Radio Hacker, which has been getting some press this year, and I hadn't used it before, so I decided to sit down and take a look at it, and it's actually pretty cool. So the way it works, we open up one of these IQ files we recorded. We then put in our samples per symbol. So this is the number of samples recorded that equals each symbol. And so in this case, it is our sample rate, the 10 megahertz sample rate that we recorded, divided by the symbol rate, which is 38.4 kilohertz. And then we can set the modulation type if it's not auto-detected, and then Universal Radio Hacker will then print out a list of likely payloads. And this actually worked very effectively, and we see all the payloads that are going from the barcode scanner to the dongle, and from the dongle back to the barcode scanner. So I then used URH to look at the 3 different IQ captures. And it turned out that in each case, it was sending the identical payload each time the barcode scanner was sending a packet to the dongle. And this is good because now we can start to look at what the actual format is. In this case, the barcodes were 12 characters long, and we have 12 bytes here in the middle that is distinct for each packet. So it looks like we just have these 12 most likely unencrypted bytes representing the keystroke data that's being sent to the computer. There's some more unique bytes on the end. This might be CRC. It's unclear because we don't know what the full format is because it's all implementation specific. So next we can see if there's a common CRC. We can run these 3 payloads through RevEnt, which is a CRC reversing tool. Unfortunately, there are no hits. This protocol for the chip does allow a 0 byte or absent CRC, so it's possible there simply is no CRC in this case. So now we can start to make some assumptions about the packet format. So it starts with a bunch of hex 5 characters. This is just alternating 1s and 0s. And so we're assuming that's going to be our preamble. This next bit, it's probably a sync field plus a header. Unfortunately, we don't have any data to tell us what that header might contain. We then have the actual barcode data sent over the air. And then we have, it's unclear what that is, perhaps a trailer, some more state data, CRC or something. And so now with doing a little bit of radio work, but mostly just using these open source tools, we've been able to determine enough information about the protocol to be able to build a receiver. So now I'm going to run this receiver script here, and this will be released online after our talk. And for the demo here, I'm going to try and read the barcode on my beer bottle. Okay, so on the right screen here, we'll have the cursor input, and this is going to be where the keystrokes are sent from the dongle when I scan the barcode. Then on the left here, we are going to have the output from a script I'm going to run, which is going to attempt to decode the data sent from the barcode reader to the dongle. Okay, so I'll scan this barcode here.
Check the terminal.
Okay, there we go. So now we're having the barcode read, and we're seeing some of the time it's picking it up on the left with SDR receiver. And what's interesting here is that because this device is just a functional USB keyboard, and this is unencrypted, it should be vulnerable to keystroke injection if you know people with barcode scanners. So now we'll take a look at this presentation clicker, which is something that looks like the Logitech R400, a common, well-known device. In this case, it's from a company called Cool. And I saw this on Amazon and ordered it to see exactly what was going on. And so this is the image on the right from the Amazon page, and it looks identical to the Logitech device. In this case, we have an FCC ID on both the dongle and the clicker. We go to the FCC docs, and I usually start by looking at the internal and external photos of a device to make sure I know what I'm looking at is correct. In this case, we see something interesting, which is it says Logitech. And this is clearly not the device we have because this is an off-brand. So this is the internal photo on the left of the Logitech dongle. This is the internal photo on the right that I took of the #China version. And you can see it's a documented Cypress semiconductor transceiver for Logitech, but a completely different board for this #China one. So this is an interesting example where you have a product which was completely ripped off. The labeling on this fake version has the same FCC ID as the legitimate one. But the problem now is that we have no idea what this unlabeled RFIC is, so we have to throw out our FCC documentation because it's for a different device. So unfortunately, OSINT failed us in this case. But we can start with a little bit of SDR work. So we're going to plug in the SDR, bring up baudline. These are 2 captures in baudline with the second half, or lower half of the 2.4 ISM band on the left, the upper half on the right. And we'll notice that when I hold down the left button on this presentation clicker, we have packets that show up on 3 different channels. So we have 2407, 2433, and 2463. And by watching the behavior of this device, we can see that it sends 1 packet on the low channel, waits 3 milliseconds, sends a packet on the middle channel, waits 3 milliseconds, sends a packet on the upper channel, and cycles back and forth. And there don't appear to be any ACKs that go from the dongle back to the clicker, so it looks like the dongle itself can camp on any one of these channels and still receive the packets. So we know that we have 3 channels in the 2.4 ISM band used by this device. Now we need to figure out the modulation. Most of these low-power devices use either on-off keying or frequency shift keying. So we can do a quick check in baudline. This is not OK. It might be FSK, but we'll need to look at it in Spectrum to see if that's the case. So this is an IQ capture from this clicker and in Spectrum. And we have the frequency plot again, which is showing us the oscillation back and forth between the 2 frequencies. We then use a cursors tool again. We're lining up those vertical lines with the oscillation points between these two frequencies, and that tells us the symbol rate. In this case, it's a nice even 1,000 kilohertz, so 1 megabit per second symbol rate. So now we know that it's FSK, 1 megahertz symbol rate. We know the channels it operates on. Now we need to figure out what the contents of these packets is. So here we have a simple flow graph to demodulate the channel that the device is operating in. So we start with our UHD USRP source. This is data coming in from the software-defined radio. That goes through a low-pass filter to filter out anything outside of the frequency band we're looking at. We then send it through the GFSK demodulator, which will attempt to demodulate that channel and send out ones or zeros. We have this repack bits block, which takes the ones and zeros output of the demodulator, packs it into 8-bit bytes, and writes that to disk. So what happens is we run this flow graph. We make some packets by clicking buttons on the presentation clicker, and then I'll have a file on disk, which is the demodulated output of the channel this is operating in. So the idea is that in that file we write to disk, we're going to have some of the packets this thing sent over the air. And I'm a big fan of using GNU core utils and other common utilities to look at these type of files. So we'll start by passing this demodulated output through XXD, and this is going to give us a hex dump on the console of everything in that file. And as we said earlier, most packets will start with a preamble. That's either alternating ones or zeros, which is AA or 5 in hex, or all ones or all zeros, so 0 or F. So we can grep for what looks like a preamble, and then look for the next 4 bytes or 8 hex characters, and then see what repeats. And then we can build this out for longer and longer sequences until we have these long repeating sequences in the file, which are likely packets. So we go through and do this, and we have this single packet from the left button on the presentation clicker that is repeated over and over again. So this tells us something interesting, which is that there's no sequence number. It's just the same data sent every time we click one of these buttons. So we can go through and repeat this process for the 4 buttons on the clicker. So that's left, right, play, and full screen. And we can see that there are some parts of the packet that are similar between each packet and parts that are distinct. So we have this one unique byte in the center, and this is likely going to be the actual byte that indicates a button that was pressed. At the end, we might have some data information and a CRC. And so we'll check for CRC next, and we put these 4 packets through RevEng. In this case, we have the polynomial 0x1021, just a common CRC16 polynomial. So this is nice because now we have a checksum that we can check when we're receiving packets to verify their integrity. So now we can start to make some assumptions about the format of these packets. So we start with a preamble. We have what we think is a sync word, 4 bytes, just a common sync word length. We have what might be a header, but unfortunately we don't have any way to know for sure. We have the button ID. We then have some more mystery bytes, we have a CRC, and then we have a trailer. And we can use this information to build a simple receiver, which we'll also post online. So let's do another demo here. So what we'll see here is that I will have, on the right console, we'll have the input again. Then on the left console, we're going to have our script, which is going to attempt to receive the packets going between the presentation clicker and its dongle and tell us what button was pressed. So I'll press the left button, we have left, right, play, and monitor, or full screen. And again, this is a case where we have unencrypted data going to the dongle. The dongle in this case is also a keyboard, so again, another interesting target to look at. And now Matt is going to take you through some overview of the project.
All right, so essentially what we've done in this session is we've introduced a methodology that you'll be able to take with you and apply to a variety of wireless protocols that you might encounter. And we've introduced 5 steps, and in looking at the devices that we looked at, we were able to show that all these devices kind of share these common elements. So for all the devices, they all had some notion of a channel represented. The barcode scanner and the security siren were both at 433. The presentation clicker was a frequency hopping protocol up at 2.4 gigahertz, but they all have this notion of a channel that you can kind of characterize. The second element is where they differ the most, and that's the modulation. However, we've been able to show that relying on open source intelligence is able to reduce the search size quite a bit, if not tell us outright what it is. Additionally, all 3 physical layers share a common notion of symbol timing. And they vary quite a bit. The security siren had a very slow symbol rate. Presentation clicker was quite a bit faster. The key element is that they're all digital modulations with discrete timing information to characterize and extract. They all share synchronization features. They look different based on the device, but they're all there for you to identify and leverage. The barcode scanner and the presentation clicker both had distinct preamble and synchronization, whereas the security siren just had a start a frame or a sync word. And then finally, once you get to step 5, you just have bits on a disk. And we're all in this room, we're all security practitioners. We all have tools and methods for working through data like this. Once you get to this stage, you can basically just apply the skill set and knowledge that you have from whether it's doing binary reversing or other types of network exploitation to this data to figure out what's actually happening at the packet level. So essentially with this process, we've been able to reduce reversing these 3 different wireless protocols, very different wireless protocols, down into 5 steps that works for all of them. So to wrap up, we've shown that these different wireless systems can be reverse engineered by using the structured process. Additionally, we've shown that open source intelligence can make your life quite a bit easier. By relying on documentation and regulatory filings, you can make this process very, very easy. Just with a little bit of research on the outset. And finally, we've shown that once you demodulate, you have bits on a disk that you can work through using any method that you choose. I like to use Python. Marc likes his command line tools. There are a lot of ways to approach this, but once you get to this stage, it'll be in a domain that you'll be comfortable with. So if you're interested in learning more about this, we're going to be running a workshop on this tomorrow. From 11:30 to 1:30, we're going to be live hacking a device. We have a restaurant pager system, like what you'd use to find out when your table's ready. We haven't looked at it yet, so it's going to be fun for all of us. We're basically just going to be walking through this methodology live, and we encourage you to bring a laptop and some software to hack along with us as we do it. So if you want to participate, please show up with a laptop with GNU Radio. If you don't want to go through the super fun process of installing it from source, you can grab the GNU Radio live USB image and flash it to a USB stick. And that has all the tools that you'll need, kind of canned and pre-installed on it. Additionally, it would be great if you could install Inspectrum and Baudline, which are 2 open source tools that are really awesome. And then we'll provide a whole bunch of RTL SDRs, which are really cheap, inexpensive software-defined radios. So if you bring your laptop, we'll bring the radios, and we'll have a party. And we'll tweet out this information. So if you don't get it on the slides right now, you'll be able to find it online later. And we'll also be at the truck momentarily if you want to talk more about the requirements there. One other note, we gave a talk at DEF CON 25 this year that you can kind of think of as being like part 2 to this talk. So this talk went through how to reverse engineer these different physical layer state machines. The talk that we gave at DEF CON basically picks up where we left off, where we're leaving off right now, and looks at how you can begin to think offensively about physical layer state machines. So both how you can attack them, and then how you can kind of use them offensively. It's called Radio Exploitation 101. There will be a video available whenever the DEF CON videos go live. So if you like this and you want to learn more, that's a good place. That's going to be a good resource to continue this with. So finally, just one last thought to leave you with. We've seen time and time again, I think Don did a very good job of introducing this morning, and we all read the news. We've seen time and time again that the Internet of Things is full of holes. And with tools like software-defined radio and modern wireless reverse engineering capabilities, you are now empowered to go out and find them. So with that, I encourage you to investigate wireless security, wireless reverse engineering. It's really not as hard as you think. So thanks very much, and we'll be happy to take your questions.